Okay, we've looked at how to represent vectors graphically in terms of pictures and how to manipulate those pictures to do vector addition and vector subtraction. Now we want to look at how to do these same things but by representing the vectors in terms of an algebraic equation. So the algebraic equation is obviously going to have to relate to the pictures, and so that's what we want to see. How do these things relate, and how do we have both pictures, both the algebraic and the geometric? One way to do that is to draw your picture of a vector, draw your arrow, and have it drawn on top or superimposed on a Cartesian plane. And so this is an XY coordinate system. So you can see the x-axis here, and the y-axis is up here. We can draw the y-axis. There's the y-axis. So we can look at our vector and we can say this vector starts at the origin and it goes to the point 4, 3. And so we could say that the sides that the triangle that this vector makes on the Cartesian plane would be to go over 4 and to go up 3, and that locates the point where the tip of the vector is. Now, this angle, if you do your basic trigonometry, you could easily figure out that this angle is 37 degrees, and by applying the Pythagorean theorem, we could say that the length of this vector is going to be 5 units, or 5 of these little squares. So the normal way that we would represent the vector would be to give its magnitude and its direction. And if you look at the Cartesian plane, you could recognize that that's like plane polar coordinates. So the normal way that we represent pictures graphically, we can define their angle and we can define their length and use plane polar coordinates to specify the magnitude and the direction of that vector. But we can also look at the point that the vector points to. And in this case, that would be the xy ordered pair of 4, 3. And so that's the point where this vector points to. And we're going to use that to break this vector into simpler vectors that point along the x direction and point along the y direction. And we'll see how that works coming up. Okay, again I have my representation of my vector r. It's on the xy plane, so I can draw in, that's the x-axis, and that would be the y-axis there. And so I have represented my vector r in terms of these two red vectors, which I'm calling r sub x and r sub y. And these are called the components of the vector r. Specifically, this would be the y component, C-O-M-P-O-N-E-N-T, that's how you spell component. This is the y component, and this would be the x component. And how are these vectors arranged? Well, if you think back to what we did previously, look at this. I've got my Rx here. I've got the tail of Ry connected to the tip of Rx. And then my vector R is from the tail of Rx to the tip of Ry. Hopefully, you recognize that as a vector addition. So this vector R is simply the vector sum of these two components, the x component and the y component. Now, what does that mean, x component and y component? Well, component means part, and so this is the part of the r vector that points along the x-axis. And this ry is the part of the r vector that points vertically up, or that points along the y-axis. And so this lets us say that the vector r is simply going to be the sum of its components. R vector is equal to Rx vector plus Ry vector. So that gives us a vector r that's been replaced by a sum of its two components. And it's important to note that because the x and y axes are perpendicular, these components are going to also be perpendicular. So this would be a right angle here, and that would make this triangle a right triangle. Okay, so I want to go off on a little bit of a tangent here. We'll get back to the picture in the previous slide, but it's important that we understand how to deal with the directions of vectors. Now, we've already seen that you could use an angle to represent the direction of a vector, but it turns out there's actually a more generalized way of dealing with vector directions, and that's to use something called unit vectors. And a unit vector is defined as a vector with a magnitude or a length 1. So a vector with a magnitude 1. Remember, the length of the vector represents its magnitude or its amount. And so 1 unit length, that's the length of the unit vector. And the reason that we construct unit vectors is that they're used to show direction. So I have a little picture here. And so I've got a vector that's in, and I know that my vector has got the little arrow on top. And typically when you're talking about a unit vectors are represented with a hat. And so notice that there's a little hat on top of the in here. And that little hat, if you're curious, is called a circumflex. That's the name of the mark, but typically we just call it the hat. And so this equation here shows me that I've got n vector. I know it's a vector because it's got an arrow on top. N vector is equal to magnitude of n. I know it's a magnitude because of the absolute value bars. And so I've got n vector is equal to n magnitude times n hat. And what is n hat? N hat is a unit vector. That is, it's a vector whose length is 1, and it points in the direction of n. And so here I see unit vector n, so I know that this length here, this blue vector, has a length of 1. How do I know that? Because there's a hat on top. That tells me it's a unit vector, which means it has a length of 1. And so if I go from here to here, that would be one unit, that would be 2 units, that would be 3 units, that would be 4 units. So I could actually write this out. I could say that n vector is equal to 4 units in the n hat direction. And so what does that do? It takes my n hat vector, which has a length of 1, and it expands it by 4 units to make a vector that points in the direction of n hat, but is 4 units long. This is what we mean when we say that n hat shows us the direction. We're always going to multiply our unit vector by some magnitude to scale it. That's a scalar, of course. We're scaling it, we're changing the length of it. But the key thing here is that this hat tells me that my vector has a length of 1, and it's used to show direction. Okay, let's summarize. We have a vector n here, and it's equal to a magnitude times a unit vector. That gives me the length, that gives me the direction, the two constituent parts of my vector. The n hat tells us the direction, and it's worth remembering that that magnitude is always going to be a scalar. It's always some number, 15, 22. Always a positive number, in fact. We're reminded of that because of those absolute value bars. Now we're going to see that you can't actually have a negative, but that's not part of the magnitude. That's part of the unit vector. And what would a minus n hat mean? It's simply a vector of length 1 that's flipped in the other direction. So if I had, an n hat like this, this would be minus n hat. And so that gives us our unit vector and our minus unit vector, which gives us the direction of whatever vector we're scaling. And so if I multiplied this by 4 or 16 or minus 133, I know how long the vector is, and I know what direction it's pointing. It's either going to point along n hat or along negative n hat. Now, we started off this video by superimposing a vector on the Cartesian plane on top of the xy axes. And in 3 dimensions, there would be an x, a y, and a z axis. And so those Cartesian directions are very commonly used in physics to represent the location of points in space. And so if we're dealing with vectors in a 3-dimensional or a 2-dimensional Cartesian axis, we need to have vectors that represent the directions of those axes, the x-axis direction, the y-axis direction, and the z-axis direction. Those are used so much that it's very common to define unit vectors that point along the different directions of the axes. And there's a couple of different standards that are very commonly used. There is the old standard, which uses I hat, j hat, and k hat, and that's how you read those, by the way, I hat, j hat, and k hat, these vectors right here. So I hat is a unit vector that points along the x-axis. J hat is a unit vector that points along the y-axis. K hat is a unit vector that points along the z-axis. This is actually the standard that is used in our textbook, and it's an older standard. You find it a lot in older books. Now, very common, more modern textbooks, or not necessarily more modern, but more textbooks that were written more recently, use a more modern standard where the coordinate axes have unit vectors labeled with x hat, y hat, and z hat. It's easy to remember the x hat vector points along the x-axis, the y hat vector points along the y-axis, and so on. I actually prefer the modern standard, so I tend to use that a lot when I'm working problems, but the older standard is still common enough that you need to be able to recognize it. X, Y, Z all go in order. I, J, K all go in order, so it's pretty easy to switch back and forth from one system and the other. And I'm going to expect you to be fluent in using both of them. So I'll sometimes work problems with the I hat, J hat, K hat. I'll sometimes work problems with X hat, Y hat, and Z hat. Your book, of course, uses the older standard. I probably will use the modern standard more often. So between the two, you should get pretty used to using both standards. It's not rocket science to go from one to the other, so I don't think you'll have any problem with that. But you really do need to know both. So let's go back to our picture of our vector r with its x and y components. Now I've added into our picture our unit vectors. Notice these green arrows here. I've got x hat, which is a vector of length 1 unit that points along the x-axis. I could have called it I hat, but I chose to call it x hat, so that's the way we're going to go today. And here is y hat, which again, I could have called that j hat if I wanted to. That would have been the other standard, but I decided to go with y hat, so we're just going to roll with that. But these unit vectors point along the x-axis and the y-axis respectively. And so I can see that my rx vector, which is the x component of the total vector r, that's going to be some length of rx in the x hat direction. So if I look at my equation that I had previously, r equals rx vector plus ry vector, that's total r vector there. Well, this rx vector is just some magnitude, which I'm calling the magnitude of rx, in the x hat direction. And this vector here is the magnitude of ry in the y hat direction. And I left a little arrow off, so I will fix that. There should be an arrow above that rx there. So that's the magnitude of rx in the x hat direction, the magnitude of ry in the y hat direction. And I've rewritten it down below, and I've dropped my absolute value bars. And so they're understood there. We can recognize if you just see, and again, this is going to be my total r vector is equal to rx x hat plus ry y hat. It's understood that rx is the magnitude of the x component, ry is the magnitude of the y component. Now, when we deal with a vector that is broken into a sum of its x component and its y component, typically it's going to make a right triangle. And so I just wanted to review some of the properties from right triangles. You guys should all know this, but let's just quickly go through it. I've got a right triangle here. We know that the right angle is represented by the little perpendicular mark there, and that right angle is opposite the hypotenuse, which is the longest side of the triangle. So the hypotenuse is always the one that's opposite the 90 degrees, and it's always the largest side of the right triangle. Now, I've got a couple of other angles here. So here's the 90-degree angle, and then here's an angle theta, and there up above is an angle phi. And so usually when we draw this on a Cartesian coordinate system, theta is the angle that we're looking at. And so we have the angles, we have the lengths of the sides. What do we know about those things? Well, first of all, we know the Pythagorean theorem. The squares of the legs of the triangle equals the square of the hypotenuse. That is, you add up the squares of the legs, you get the square of the hypotenuse. And so that means that this side a squared plus this side b squared is going to equal the square of side c. I'm sure you all know the Pythagorean theorem, so I'm not going to spend a lot of time on that, but I just wanted to remind you that you do in fact know it. And then in terms of the angles, we know that the angles are related to the lengths of the side by the sine, the cosine, and the tangent of those angles. And those are defined such that the sine of theta is the opposite side over the hypotenuse. So here's theta. The side opposite of theta is b. The hypotenuse is c. So the sine is defined as b over c. The cosine is the adjacent side divided by the hypotenuse. So that gives me a over c. Adjacent over hypotenuse is a over c. And then the tangent is the opposite over the adjacent. So the tangent of theta is going to be the opposite b divided by the adjacent a. That a is adjacent to theta. And so you guys need to know those definitions. You probably learned some mnemonics in your trigonometry class. You might have learned SOHCAHTOA, which may not be politically correct these days, but they would say that that was the trigonometry Indian chief SOHCAHTOA. I learned Oscar, so you might know this one. You say that the sine divided by the cosine equals the tangent, so that gives you the order, SCT, sine over cosine equals tangent. That is, by the way, a way that you can define tangent. And then it's Oscar had a heap of apples. And you can see that's where the SOHCAHTOA comes from, if you learned it that way. But that's just a mnemonic to remind you that for the sine, it's the opposite over the hypotenuse, opposite over hypotenuse. For the cosine, you get the adjacent over the hypotenuse. And for the tangent, you get, obviously, the opposite over the adjacent. And so those give you the definitions of those functions, sine, cosine, and tangent. And with the Pythagorean theorem, you can completely understand all the parts of that right triangle. Now, I wanted to mention one last thing. We have the angle theta. That's the angle that you're going to have probably 9 times out of 10. But maybe 1 time out of 10, you're going to have the angle phi. And when you have phi, it's different because A is no longer the adjacent side. It's the adjacent to theta. But for phi, it's the opposite side. B is now the adjacent side to phi, whereas it was the opposite side of theta. So what that means is that if you have the angle phi, your sine and cosine are going to be backwards. In fact, you have to be very, very careful when calculating these. Here is my advice. Whenever you have to use trig, take a second, draw the triangle and look at where the angle is, figure out what's opposite, what's adjacent, what's the hypotenuse, and apply your trig that you know. If you just get in the habit of always assuming that one is sine and the other is cosine, you're going to be tripped up when you have the angle that's opposite to the one you're used to dealing with. So just be very careful about which angle you have and apply the definitions that you know. So here I have that triangle written again, and if we look at phi, we can see the opposite is A, and the hypotenuse is still C, so the sine of phi is going to be A over C. That's not what it was in the previous slide because we were looking at theta, not phi. But the cosine of phi is going to be the adjacent over the hypotenuse, that gives me B over C, and then of course the tangent of phi is going to be the opposite over the adjacent, which gives me A over B. So it's completely different from the sine. In fact, everything's kind of flipped around. So you want to make sure that you draw your triangle, look at where your angle is, and apply the definitions. In this slide, there's a summary of all these relationships. Now, we have picked a way of writing them out that's going to be very useful for us. The first thing that we can note is that with this triangle, and we're dealing with theta again, so theta is the angle that the vector makes with the positive x-axis, and we can say that the magnitude of r sub x, that's going to be the adjacent side, divided by the magnitude of r, that's the hypotenuse, adjacent over hypotenuse, that is the cosine of theta. So what does this equation give us? This equation here links the x component and the original vector r. And so we know that Rx is related to the original vector r by the cosine of theta. Now, if I look at the opposite side of the angle, Ry, I know that the opposite over the hypotenuse is equal to the sine of theta. And so that equation here, that links up the y component with the original vector r. And so if I know the angle theta and I know the length of the original vector, I can figure out what the two components Rx and Ry are. That's the way to think about this. Now, down below, what if we have the reverse? What if we know what the components are? Well, we can use our trig to figure out what the angle and the magnitude of the original vector should be. We know that from our trig that theta is equal to the arctangent of Ry over Rx. Ry would be the opposite, Rx would be the adjacent. So we can say that Ry over Rx is equal to the tangent of theta. And then the arctangent is the inverse function that gives you the angle from the tangent. And so, in other words, if I tell you that the tangent of 22 degrees is equal to 0.404, you know what that means, and that's the ratio of the opposite side to the adjacent side of a 22-degree angle in a triangle, in a right triangle. But if I tell you that I've got this 0.404 and I take the arctangent that's going to give me 22 degrees. And so in other words, I can take the tangent of the function and get the decimal that represents the ratio of the sides, or I can take the arctangent of the ratio of the sides, and that'll tell me what the angle is. And so this is what we're doing here. We've got our components y and x, and we want to find theta, so we take the arctangent of that ratio. And then, of course, if I want the magnitude, I can simply apply the Pythagorean theorem. In other words, this side squared plus that side squared is equal to the square of the vector. There's a lot in this slide to unpack, so let's go through it real quick once again. If I know what the magnitude of the original vector is and the angle, I can use these relationships here to get the components Rx and Ry. If I know what Rx and Ry are, I can use these relationships to get the angle and the magnitude of the main vector. And so we're going to have some opportunities to practice this, but I want you to get the main ideas down. Before we go on, though, I want to mention one more thing. Very often we use the Cartesian coordinate system to define the angles that show the directions of these various vectors. But sometimes it's very convenient to use the ordinal directions of a compass. And so I've drawn in what looks like a Cartesian coordinate system, but instead of labeling it with x and y, I've labeled it with unit vectors pointing in the east, the north, the west, and the south. And typically I can represent a vector A on this compass directions map by two different angles. And so I could, for example, to begin with, use the normal angle. So I'm going to consider this angle here. And we would say, if I wanted to call that angle theta, we would say that theta is to the north of east. North of east. Because I'm starting along the eastward direction and I'm rotating my vector towards the north vector there. And so that would be my theta, and we would say that's north of east. Now, I could also start at the north axis and go down, and I might call that vector phi. And I would say that phi would be east of north, because I start at the north vector and I rotate down towards the east. And so that would be east to the east from the north. Theta would be to the north from the east. And so we can pick any direction that we want. So if I wanted to do something like this, I had a vector like that, and I wanted to know what would the direction of that vector be. Well, here I've got the west, here I've got the south. That would be south of west. Now, one little thing here, a caveat, if the angle is at 45 degrees exactly, this angle we would say is northeast. This angle, if it's exactly 45 degrees, we would say is southeast, etc. And so if I say something's moving in a southeastern direction, then you would say, oh, it's at a 45 angle down that way. But if I said an angle is going at 30 degrees west of north, you can figure out where that would have to be and what it would mean. Okay? So you'll get some opportunities to practice with this, but I just wanted to explain this basic approach because we will use it some, although mainly we'll be using the Cartesian coordinate method that we talked about at the beginning of this slide. Anyway, that is the end of this video, and we'll go on and keep going with the next one.